Molecular orbital theory was first developed by F. Hunt and R.S. Mulkin in the year 1932. Bonding molecular orbitals are represented with sigma and pi, whereas anti-bonding molecular orbitals are represented by sigma star and pi star. Always lower energy has to pair with lower energy. Lower energy, it never paired with or never bonding with higher energy. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Chemical Bonding and Molecular Structure. In that, we have discussed about the postulates of valence shell electron pair theory, and we have discussed about the geometry of the molecules which are having no lone pairs of electron, and also we have discussed with few examples which are having 2 or 1 lone pairs of electron. In addition to that, we also discussed about the prediction of shape of the molecule by valence shell electron pair theory. Today, let us move on to the next topic of this unit by understanding the molecular orbital theory. Okay, and in that we are going to understand formation of molecular orbitals of combinations of atomic orbitals, and we are going to understand the conditions which is necessary for the combinations of atomic orbital, and we are going to understand energy level diagram of molecular orbital, and we are going to discuss with the bonding in homonuclear diatomic molecule, and finally we are discussing about the hydrogen bonding and its type. Okay, let's see what are molecular orbital theory states. Molecular orbital theory was first developed by F. Hunt and R.S. Mulkin in the year 1932. So, according to them, they have given the certain postulates about the molecular orbital theory. According to that, the first postulate says that when atomic orbitals are combined directly, which leads into the formation of molecular orbitals. What does the first postulate says that? When atomic orbitals, when it is combined, leads to the formation of what? Molecular orbital. This was the first postulate. And second postulate says that molecular orbitals are in the region in the space where the probability of finding the electrons in the is maximum in a molecule. Suppose if the molecular orbitals are oriented in a space, the probability of finding the electron which is there in each atomic orbital, it's very easy according to the molecular orbital theory. And atomic orbitals of comparable energy and proper symmetry can combine to form a molecular orbitals, and atomic orbital is a monocentric, whereas molecular orbital is polycentric. So, this is another important thing that you must keep in mind. Then, number of molecular orbitals are equal to the number of combining orbital. When 2 atomic orbitals are combined, 2 molecular orbitals are formed, then it is known as bonding molecular orbital, while others are known as anti-bonding molecular orbital. So, these are the first important molecular orbital theory silent features. What does the first silent feature say is that according to it, atomic orbitals will be combined to give a molecular orbital. And when we oriented this molecular orbital in a space, it gives us to what? It gives the idea about probability of finding the electrons. Okay. When atomic orbitals are having same energy with the same geometry, they combine to form molecular orbital. Suppose we have 2 sets of molecular orbitals that is formed by 4 atomic orbital, and it is known as bonding and antibonding molecular orbitals. Okay. Next is bonding molecular orbitals have a lower energy, hence it is a greater stability than corresponding anti-bonding molecular orbitals. Always remember, when it is form a bonding molecular orbital, it is always stable as it is compared with anti-bonding molecular orbital, and bonding molecular orbitals are represented with sigma and pi, whereas anti-bonding molecular orbitals are represented by sigma star and pi star. Okay, each molecular orbitals can accommodate the maximum of how many electron? 2 electron. Okay, then the molecular orbitals like atomic orbital can be filled according to what? According to the Hund's rule, Hufbauer principle and Pauli's exclusion principle. So we already have understood that how the electron will be filled to the each orbitals, especially to the each atomic orbital according to the Hufbauer, Hund's rule as well as the Pauli's exclusion principle. So based on this, we have to fill only 2 electrons to the each atomic orbital. Okay. So let's see with their example so that we will understand how the bonding and anti-bonding orbitals, which is also involved in the formation of molecular orbitals. Okay. Now the formation of molecular orbital, that is linear combinations of atomic orbital, which is also known as what? LCAO. Let us consider the hydrogen molecule consists of 2 atoms A and B. Each hydrogen atom in the ground state has how many electrons? 1 electron. And atomic orbitals of these atoms can be represented by the wave function known as psi A and psi B. Mathematically, the formation of molecular orbitals are described by linear combinations of atomic orbital which take part in addition and subtraction of the wave function. Okay. So remember, if I write the hydrogen, we know that hydrogen has only 1 electron. Is it right? So if I say it is hydrogen molecule, it consists of 1 is 2 electron. Is it right? And if you are writing this in LCHO, LCAO, the wave function used to measure the LCAO. Next is formation of molecular orbitals by using what? Linear combinations of atomic orbitals. Already I have explained that. So we use a wave function known as psi A and B because we are studying about the hydrogen molecule. Is it right? Yes. So sigma is equal to psi A plus psi B, whereas sigma star, which is the anti-bonding molecular orbitals, which is given by psi A minus psi B. So the molecular orbitals sigma, which is formed by addition of atomic orbital, that leads to the formation of what? Bonding molecular orbital, whereas the sigma stars are formed by subtraction of atomic orbital, hence it is known as anti-bonding molecular orbital. So qualitatively, the formation of molecular orbitals can be understood in terms of constructive or destructive interferences of the electron wave of combining elements or combining atom. You can here see that how I have represents the MOT by taking hydrogen molecule as an example. So this is the energy. You can see that this is a psi A for atomic orbitals of hydrogen atom and psi B is the atomic orbitals of hydrogen atom. Okay. These two are the hydrogen atom. So when it is combined, leads to the formation of what? So leads to the formation of sigma bonding atomic orbital. It is a bonding orbitals which is having lower energy and it is highly stable. You can see that this is a sigma star which is obtained by what? Psi A minus psi B, and these two are the molecular orbital. Always remember these two are the atomic orbitals. Okay. So antibonding orbitals are higher energy than that of the atomic orbitals. This is how we generally represent the each molecule by taking MOT. Okay. So first we need to mention the atomic orbital when it is combines to form what? Molecular orbital. So it will be sigma as well as with a sigma star. So sigma star is an antibody. Sigma is a bonding. Okay. Next is I'm talking only about bonding molecular orbital. Let's see how does it will be formed once again. So in the formation of bonding molecular orbital, the two electrons wave of the bonding atom reinforces with each other and causes a constructive interferences. As a result of this, electron density in bonding molecular orbitals will be located between the nuclei of the two bonded atom, because of which repulsion will be exist between the nuclei, which is very less, and electron which is placed in bonding molecular orbitals tends to hold the nuclei together and stabilizes the molecule. Here you can see this. This is a one hydrogen atom and another hydrogen atom having a plus charge. When it is combined, it forms what? Bonding orbital. This shows that the bond is the region of constructive interferences, which means that the two atoms which is held by the molecular orbital, especially at the nucleus. Next, in case of antibonding molecular orbitals, what will happen? The formation of antibonding molecular orbital, the electron waves are cancelled with each other due to the destructive interferences. So in the last case, we have understood that due to the constructive interferences, they form a what? Molecular orbital. But here, due to the destructive interferences, they cancel with each other, and most of the electron which is located away from the space between the nuclei. So this is known as nodal plane. Okay, this is a nodal plane where electrons will be get cancelled with each other and results in a formation of antibonding regions. This is mainly due to the destructive inferences. Okay. Next, let us see which are the conditions are required for the combinations of what? Atomic orbitals. So what does the first condition says? The combining atomic orbitals must have what? Same and nearby same energy. This means that the 1s orbital can combine with another 1s orbital but not with the 2s orbital. So it is clear from the first statement that always lower energy has to pair with lower energy. In lower energy, it never paired with or never bonding with higher energy. So each atomic orbital, when it is combining, it should have what? Same energy. Next, the combining atomic orbital must have same symmetry about the molecular axis. For example, 2px orbitals of one atom can combine with 2px orbitals of another atom. It is very clear. This indicates that the second condition, whatever the atomic orbitals which is there, which is having same energy, it should also have same symmetry. For example, if you write 2px, it should bind with what? 2px only, not with 2py or with 2pz. Okay, it should always bind with what? Same symmetry. Then only the bonding will be more effective. The combining atomic orbital must overlap to the maximum extent, and greater extent of overlap, that greater will be the electron density between the nuclei of the molecular orbitals. So when atomic orbitals, when it is overlapped together, what will happen? So we know that we get a molecular orbital. When they overlap with a greater extent, the electron density between the two nuclei in the molecular orbitals, it is also become greater. So these are the three important things are necessary, or the conditions which is necessary to form a molecular orbital from the atomic orbitals. Okay. So now let us see energy level diagram for molecular orbital. So how do we represent the energy level diagram? So here I have listed out the energy level diagram. So it will be starts with 1s, which is less greater than sigma star 1s, then sigma 2s, sigma star 2s, then sigma 2px, which is greater than pi 2px, which is equal to pi 2py. Similarly, which is greater than pi star 2px and pi star 2py, and finally sigma star 2pz. So this order will be applicable only if the atomic number of the element which is greater than 7. For example, you can see that in the oxygen, how many electrons will be there? 8 electrons will be there. Similarly, in the fluorine, how many electrons will be there? There are 9 electrons will be there. So the elements whose atomic number is greater than 7, those elements will have this order of writing the energy level. Okay. Sigma 1s, then sigma star 1s, then sigma 2s and sigma star 2s, which is greater than pi 2px, which is equal to pi 2py, which is greater than 2px, which is greater than pi star 2px and pi star 2py, then sigma star 2pz. So this is applicable to the element which are having the atomic number which is lesser than what? Lesser than 7. You can list out the many examples for this year, where you can take the lithium molecule, beryllium molecule, boron molecule, carbon molecule are those examples where all this element have their atomic number which is lesser than 7 and it have their own energy level. So hope you all understood with these two. If you have understood this electronic configuration or the energy level, you can easily fill the electron with the given element. Okay. Next, what is this electronic configuration and molecular behavior? The distribution of the electron among the various molecular orbitals are known as what? Electronic configuration of the molecule. So in the electronic configuration, we have understood that how we will distribute the electron to the each molecular orbitals. Is it right? That is why it is known as electronic configuration of that given molecule. Then stability of the molecule, that is also decided by if the NB means number of electron which is present in what? Bonding atomic orbital. Okay. Bonding atomic orbital is the number of electron which is occupying in bonding orbital, and Na is the number of electron which is occurred in anti-bonding atomic orbital. If the molecules is stable, then you say NB must be greater than Na. So if the molecules are stable, we say that NB is greater than Na. If the molecules are not stable or if it is unstable, we say that NB is less than Na. What is that NB and Na again? So NB and Na are nothing but a number of electrons which are involved in bonding and number of electrons which are involved in what? Anti-bonding molecular orbitals. This is how, by using this energy level diagram and also by writing the electronic configuration, we can easily understand that which element will be more stable and which element will be less stable. So based on which concept? Based upon the number of electrons which are present in bonding as well as the number of electrons which are present in anti-bonding molecular orbitals. Bond order. So how to calculate the bond order? For this, we have a formula here. The bond order will be obtained by Nb minus Na divided by 2. What is that Nb and Na? Just now we have discussed that Nb is the number of electrons which is present in bonding orbitals, whereas Na is the number of electrons which are found in anti-bonding molecular orbital. If you subtract these two and divide it with the 2, you will get a bond order of particular element. Like that, we can also calculate the bond length. So bond length will be decreases as the bond order will be get increased. Then magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, then substances will be diamagnetic, and if the one or more molecular orbitals are singly occupied, they are paramagnetic because they are attracted towards the magnetic field. If one or more atomic molecular orbitals are singly occupied, we say that they are attracted towards the magnetic field, hence it is named as paramagnetic. If there is no molecular orbitals which are having no electron, such bonding orbitals are also known as diamagnetic because they repel from the magnetic field. So these three things we can easily decide. One is bond order, bond length as well as their magnetic characters based upon the electron distribution. Okay. Now let us take the first example. That is bonding in some homonuclear diatomic molecule. I have taken out the example of hydrogen molecule. Okay. It is formed by combinations of two hydrogen atoms. We know that each hydrogen atom has how many electrons? One electron in its valence shell. All these are two electrons in two hydrogen molecule, which represents the sigma 1s molecular orbitals, and so the electronic configuration of hydrogen is sigma 1s square. So how do we write the electronic configuration of hydrogen atom? We know that the hydrogen atom will have an electronic configuration of 1s1. Similarly, if you write another hydrogen atom, it is 1s1. Together, if you write for the hydrogen molecule, we write 1s2 because one electron will be added to get a 2 electron. Okay. Then, how to calculate the bond order? We know that bond order will be calculated based upon the distributions of the electron to the bonding and antibonding. Here you can see that this is the energy level diagram. You can see that this is a atomic orbital and this is a one atomic orbital. You can see that these two are the hydrogen atom. When it is shared one electron, it becomes what? Hydrogen molecule, and we know that this is a molecular orbitals of hydrogen molecule, and there will be no electron in the antibonding molecular orbital. Is it right? From that, we can easily say that there are two electrons which is present in bonding atomic orbital, whereas in antibonding there will be no electron, so it is 0. So it is 2 minus 0 divided by 2. So it will be like this. So it is 2 by 2. If you cancel with each other, you will get 1. This indicates that between two hydrogen atoms, we have a single bond. So between the two hydrogen atoms, we have a single bond, and it is a covalent bond, since you can see that there will be no unpaired electrons are there. Hence it is diamagnetic in nature. They are not attracted towards the magnetic field, they repel from the magnetic field, hence it is diamagnetic in nature. Like this, all these things you should mention if they have given any homonuclear diatomic molecules. We'll discuss with another example. I'll go with the helium molecule. Again, we know that helium molecule which consists of 2 electrons, is it right? And we write as helium which is equal to 1s square. Similarly, another helium atom which consists of how many electrons? 2s square. So, total it is sigma 1s square and sigma star 1s square. Is it right? Yes. So, here you can see that this is a helium atoms. So, these two are the helium atomic orbitals will having 2 electron. When it is shares, it forms what? Bonding atomic orbital, and when it is shares another one electron, it also forms a anti-bonding atomic orbitals. Is it right? Yes. So, here you can see that we have 2 electrons in the bonding and the 2 electrons in the anti-bonding molecular orbitals. And how to calculate the bond order now? So, bond order will be obtained by what? Half into Nb minus Na. So, it is 2 minus 2, and you can write it is 0 by 2. Anything by 2, it is nothing but a 0 only. Helium molecule is unstable and it do not exist, and it is monoatomic molecule. It is a monoatomic molecule and it does not exist in dimeric form. Okay. This is how we can clearly understand it from its electronic configuration, and by writing the bond order, we can understand their nature. Next, we will see with the lithium molecule also. We know that lithium which consists of how many electrons? 3 electrons. So, it consists of 3 electrons. In its outermost shell, it has only 1 electron. Is it right? And the electronic configuration of lithium atom will be goes like this. It is 1s square, 2s1. So, totally how many electrons will be there here? You can see that 1s square and 2s1. Totally, there are 6 electrons will be there. Is it right? Yes. So, there are 6 electrons will be there in the lithium molecule. You can count here 2 plus 1 and 2 plus 1. Totally 6 electrons are involved in the bonding. So that the electronic configuration, which is also written as K into K sigma 2s square, where Kk stands for closed K shell structure. It means that lithium molecule is stable and it has no unpaired electron. How do you say that no unpaired electron? You can see that this is a lithium atom and this is another lithium atom which shares 1 electron to form a bonding atomic orbital. When it shares another 1 electron, it also forms a anti-bonding atomic orbital. Similarly, I'll go with the 2s. We know that in the 2s it has only 2 electron. So it will share 1 electron to form a bonding atomic orbitals in the 2s. So it is sigma 2s, and you can see that there will be no electrons which is involved in anti-bonding atomic orbital. Hence, it do not contains any electron which is there as unpaired, or you can say that there will be no electron in the S shell also. Okay, so that bond orders can be calculated. So how many electrons will be involved in bonding here? So here it is 2, here it is 2, it is 4, minus how many anti-bonding here? Only 2, and at the 2s there will be no anti-bonding, it is divided by 2, minus 2. So it is 4 minus 2, it is 2. So 2 divided by 2 is 1. So this indicates that between the lithium atom there will be a single covalent bond, and since it do not contains any unpaired electron, they are diamagnetic in nature. Okay. We'll discuss with another one example by taking carbon as an example. I'll go with the carbon. We know that carbon has how many electrons? 6 electron, and their electronic configuration will be 1s square, 2s square and 2s2. Is it right? Yes. Similarly, I'll consider another one carbon atom. So it is also having electronic configuration of 1s square, 2s square and 2p square. And totally how many electrons are involved? 12 electrons will be involved, and electronic configuration of the each carbon atom can also be written in this way, that is sigma 1s square, sigma 1s square, sigma star, and sigma 2s square, sigma star 2s square, and pi 2px square and 2py square, or you can write k into k, that is closed k shell, sigma 2s square and sigma star 2s square into pi 2px square into pi 2py square. So here you can see that. So this is the MOT structure of the carbon. You can see that I have started with 2s directly. So you can see that. So there are 2 electrons will be involved in 2s orbitals. When it is give rise to 1 electron, it gives rise to what? It gives rise to the bonding atomic orbital. Similarly, it will share 1 electron to form a anti-bonding atomic orbitals. Then, if it is comes to the 2p. So, in 2p we have how many electron? 4 electron. Is it right? Yes. 2 electrons from one carbon atom, 2 electrons from the another carbon atom. When it is shares, it will form pi 2px and pi 2py. You can see that the pi 2pz is empty. Similarly, the pi star 2px and pi star 2pz is also empty. So this indicates that when you are looking at this diagram of the carbon, so how many bonding electrons will be involved, bonding atomic orbitals will be involved here? You can see here 2 plus 2. So totally there are 8 electrons will be involved, minus how many are there? 4. So it is 4. So it gives us to the bond order of 2. So this indicates that in case of carbon, which is diamagnetic in nature, it is very important to know that the carbon bond in C2 molecule consists of both pi bond, and because of the presence of 4 electron with the 2 pi molecular orbital, and most of this molecule are double bonded and made up of sigma bond and with a pi bond. So this is actually which has happened when you are considering with the carbon molecule. Okay. Next, I'll go with the oxygen molecule. So in oxygen molecule, we know that totally there are 8 electrons will be there, and electronic configuration will be goes like this: 1s square, 2s square and 2p4. So how many electrons will be involved in each oxygen atom? 8 electrons. So totally if you write the oxygen molecule, so there are 16 electrons will be involved. Is it right? Yes. And the electronic configuration will be goes like this: 1s square sigma star 1s square sigma 2s square sigma star 2s square and sigma 2p z square and pi 2p x square and pi 2p y square into pi star 2p x1 and pi star 2p y1. We'll see the structure now. So here also I have written from the 2s directly. So it will share 1 electron to form a sigma 2s, and similarly when it shares one more electron, it forms both bonding and anti-bonding molecular orbitals. Similarly, if I go with the 2s, how many electrons are become unpaired? So there are, you can see that these two and these two. So there are 4 electrons will be become unpaired. So what will happen? So it will share one electron to form a sigma 2px. Similarly, it will share one more electron to form a pi 2px and pi 2py. And similarly, that last one electron, if it is combined, results in a formation of 2 unpaired electron and is known as pi star 2p x1 and pi star 2p y1. Now, if you calculate the bond order, so how many electrons are become bonded here? So 10 electron minus 6 electron, so you will get a 2. So this indicates that between the 2 oxygen atoms, we have a double bond. Okay. And since it consists of 2 unpaired electrons, they are paramagnetic in nature because they are attracted towards the magnetic field. Next is hydrogen bonding. So this is the last concept of this unit. So let's see what is hydrogen bonding now. Hydrogen bonding can be defined as it is the attractive forces which binds the hydrogen atoms of one molecule with the electronegative atom. So it's a kind of attraction between the hydrogen with a more electronegative atom. You can take the example of water molecule. In between the water molecule, you can see that there will be a formation of what? Hydrogen bonding. So since our oxygen is electronegative in nature and hydrogen is electropositive in nature, since because of the opposite charges they are attracted towards themselves and forms what? Hydrogen bonding. And we usually represent this hydrogen bonding by writing a dotted line or by writing a solid line also. And there are of 2 types of hydrogen bonding. One is intermolecular hydrogen bond and another one is intramolecular hydrogen bond. Let's see what is intermolecular and intermolecular hydrogen bonding. So intermolecular hydrogen bonding will be formed between 2 different molecules of same or different compound, and for example hydrogen bond will be caused in a HF molecule or in the alcohol as well as in the water molecule, etc. So I'll go with the HF molecule. So between the 2 molecules, if hydrogen bonds are formed, then we say it is inter. We say it is what? Inter. What is inter stands here? Inter stand means between 2 molecules. If it is there within the molecule, we say it is intra. If it is between 2 molecules, we say it is inter-hydrogen bonding. It is always occurred between same or different molecules also. I'll go with intramolecular hydrogen bonding. It is formed by hydrogen atom in between the 2 highly electronegative atoms present within the same molecule. For example, in orthonitrophenol, hydrogen is found between the oxygen atom. Here you can see that in orthonitrophenol, you can see that hydrogen which exits between the 2 electronegative oxygen atom. So this kind of bond which is found within the molecule, hence it is known as intra. If it is found between 2 molecules, we say it is inter. If it is found within the molecule, we say it is intramolecular hydrogen bonding. Always remember, if I say it is hydrogen bonding, it is occurs between the electropositive element to the electronegative element. So it may be oxygen or with the halogen atoms also. So by this, I like to say that this is the one of the smallest and easiest unit for your first PUC, and have a look with all this concept which I have explained in a 7th session. So I'll come back with a new unit. Till that, take care, be safe. Thank you.